In this video, we solved problem number 1 from quiz number 2 from the spring 2021 semester. This was on one form of the quiz, was not on everyone's quiz. So the students who saw this problem, I first want to say that this problem is difficult to solve using the methods that we've talked about in this class. So I'm going to give you full credit. I'm going to give you an A if you can separate the variables, and then just show, well, if you can separate the variables, if you can write the differential equation in terms of the variables v and x, and then go on from there. I pulled this problem from a book. I modified it a little bit, but unfortunately I pulled it from a section that was just asking the student to classify which method would be appropriate. You were supposed to classify it as homogeneous polar, but the textbook authors, when they wrote this problem, they never had any intention of a student solving it. And you'll see why. The integration is really difficult for the integral involving v. You'll get full credit if you made it to that point. But I want to show you how to do the very beginning of the problem. So the problem statement says, show that the differential equation is homogeneous polar, find an implicit solution to the dE. We're not actually going to do that. But first, let's talk about how to show that a differential equation is homogeneous polar. There are 3 ways to do it. If you can write the differential equation in this form as m of xy times dx plus n of x and y times dy equals 0. If you can write that equation in this form where m and n are homogeneous functions of the same degree, and we'll talk about what that is in just a moment. Then the differential equation is homogeneous polar. Now, if I take this equation and I rearrange it so that dy dx is by itself, and I'm not really worried about these labels. I'm calling that function m and that function n. But if I write this instead as a quotient of 2 functions f and g, where f and g are homogeneous functions of the same degree, then the differential equation is homogeneous polar. And then the third way that we can show a differential equation is homogeneous polar is that we can write the derivative as a function, and I'll call that function h, of y over x, and actually x over y would be fine as well. If you can write this right-hand side of this differential equation as an expression that only involves y over x's, you don't have any y's by themselves or x's by themselves, you've got y over x it's being operated on. If you can do that, then it's homogeneous polar. Now, this is the form that we need to write the differential equation in so that we can solve the differential equation. So we will verify that the dE is homogeneous polar using this method. But these first two are equivalent to each other. Since this one is closer to this one than this one is, I'm going to write this differential equation in this form and verify that the dE is homogeneous polar this way. And then we'll show that if the differential equation is homogeneous polar this way, well, at least in this particular case, we can write this function on the right-hand side as a function of y over x only. And so that's the plan. So I'm going to use method number 2 and method number 3 here to show the dE is homogeneous polar, but 2 and 1 are really equivalent to each other. So let's say that we're going to use method number 2. And that requires getting dy dx by itself, which isn't too bad. It's just multiplied by this function of x and y. So let's just divide both sides of the differential equation by that function of x and y. Okay, So if I'm thinking of this as a quotient now, f of x, y is this function, and g of x and y is this function. Now I want to verify that those are two homogeneous functions of the same degree. That requires recalling this definition. Remember, we say that f is a homogeneous function of degree n if the following is true. If f of tx and ty is t to some power times the original function f of xy. A lot of students are like, what's that? Well, all it is us replacing x with tx and y with ty. If you can do that and simplify the expression and factor out a t to some power, then that function is a homogeneous function of degree n, and n is the power that you get right there. So we just want to see if f and g are homogeneous functions of the same degree. And it says, show that the differential equation is homogeneous polar. So we know that they should be homogeneous functions of the same degree. So let's actually prove that that's true. So let's show that f and g are homogeneous functions of the same degree. All right, so we have f of x and y is just y. We're replacing x with tx and y with ty. And I'm thinking of this now not as t times y, but t times y, and y is actually f. So f is a homogeneous function of degree 1. Because the power of t that's multiplying this here is a first degree. Well, it's t to the first power. Okay, so now we want to see if g is also a homogeneous function of degree 1. Now g is the function in the denominator. We want to replace x with tx and y with ty. I like to use this little placeholder notation. And then we simplify where we can. Now ty divided by tx will just give me a y over x there. The t's will reduce. So now I've got tx times e to the y over x minus ty. And then if I look at this expression and this expression and I look for what they have in common, they have a t in common. So let's factor that out. And then we ask ourselves, is that the original function g? And it is. So that is a t to the first times g of x and y. So this can be written this way. So that means that g is a homogeneous function of degree 1. And since those are homogeneous functions of the same degree, that means the differential equation is homogeneous polar. Okay, now we've done that. We could also use method number 3 to show that the differential equation is homogeneous polar. And method number 3 is important because it's actually the first step in the method for solving a homogeneous polar equation. So now let's do the same thing using method number 3. So what we want to do is we want to write the right-hand side of the differential equation, or we want to write dy dx as a function of y divided by x. So I'm taking this and I wanted to write it as y over x, and I've got this y in the numerator. In order to make that a y over x, I would have to divide it by x. So I think the easiest way to write this in the form we have right here is to just divide the numerator and denominator of the entire well, this entire numerator and this entire denominator by x, because that would give me a y over x up here. And generally, you're going to divide by x to the n, where n is the degree of those homogeneous functions. Now, in the denominator, I want you to see that every term down here, or every expression that you're adding and subtracting from each other, we're thinking of those like terms in a polynomial. They're not polynomial terms, but still, you know, the, the terminology is still appropriate, I think. We're taking each of these pieces and we're dividing them by x. So we have x over x times this exponential minus y over x. And the x's reduce. And now I've got a y over x over e to the y over x minus y over x. So that is a function of y over x only. Okay, great. Now that we've written the differential equation in this form, we would solve it by letting v equal y over x, and we solve for y. So y is equal to v times x, and then we compute dy over dx using the product rule. And then after we do, we can write this differential equation in terms of v and x only. So y is a function of x, and of course we have x here. So because of this dy dx, that means y is a function of x. So if I've got a function of x divided by x, that means v is a function of x. So that means that y is equal to v times x, where v is a function of x. And by the product rule, dy dx is the derivative of the first times the second plus the derivative of the second times the first. So now we have enough to write this differential equation in terms of v and x only. Now this is actually where we're going to stop, because we'll see that we can't actually finish the problem, because the integration on one side is very challenging. And the way we write the differential equation in terms of v and x only is we make replacements. We're substituting. We're going to replace dy dx with dv dx times x plus v. And we're going to replace y over x with v. There we go. So we've got this. And we substitute dv dx times x plus v over here. And then over here we have y over x is v. So that's a v over e to the v minus v. And then at this point, we would typically separate the variables and solve this separable differential equation. Because when we make this substitution, because the differential equation is homogeneous polar, it will always be separable. So in order to do that, we need to subtract this v from both sides. And I think I'll write this way. X times dv dx equals v over e to the v minus v. We're subtracting v from both sides. I want a 1 in that denominator. Now, in order to separate the variables, I'm going to need to take the reciprocal of both sides. And that's because I've got a function of x here, and it needs to be multiplied by a dx, and the dx is in the denominator. I need it to be in the numerator. So I'm going to have to flip that side. That's fine as long as I also take the reciprocal of the right-hand side. But we need to write the right-hand side as a single fraction in order to take that reciprocal. You can't just flip this and flip that. Then the statements won't be equivalent. We actually have to take the reciprocal of both sides. And that's easiest if we get a common denominator first. So we've subtracted this from both sides. Now we get a common denominator. And I'll use RHS for right-hand side. And the common denominator of 1 and this is just this expression here. So we have x times dv dx equals v over this expression. And then if we distribute that negative v, we have negative v times e to the v. Negative v times negative v is positive v squared. And now that we have a common denominator, we can add the numerators. I think that you can probably see why this would be a difficult integral to evaluate. Okay, so we've almost separated the variables. In order to separate the variables, we're going to take the reciprocal of both sides after we've gotten a common denominator on the right-hand side. Because if this fraction, or if I'm thinking of this product as a fraction, this fraction equals this fraction, I can flip both sides and they're still going to be equal. So I'll think of that x as itself over 1. When I take reciprocals, I've got 1 over x. I'll have dx over dv over here. And then we flip this side as well. It's looking worse. Who wants to integrate that? Not me. Then we'll multiply both sides. I guess we're just anti-differentiating that. Multiply both sides by dv. And those sort of undo each other because of the definition of the differential of x. X dv times dv is the definition of the differential of x. And so we've got this. Now we've got our x's over here and our v's over here. So we would anti-differentiate both sides with respect to the variable that is on that side. And this is where I'm going to tell my students, you can go ahead and stop. Well, on this side, if you want, you can evaluate that antiderivative. But this integral is extremely difficult to evaluate. I haven't even gone to Wolfram Alpha yet to check and see what that antiderivative would be. But using all the methods that we've taught you in Calculus 1, 2, and 3, this is not one that's easy to solve just by making a substitution or using integration by parts. And even using combinations of integration by parts and U substitution and partial fraction decomposition, it's just really not obvious how we would evaluate that antiderivative. So I'm sorry that I gave you a problem that could not be completely solved. I just took it out of a textbook and I just took it from the wrong section of the textbook. They just wanted you to show that it was homogeneous polar, and we were able to do that. But this is too difficult for us to evaluate. Okay, so let's say that we could evaluate that. Then we would have a function of v over here equals this. So I'm just going to write this for right now. So I'll say g of v plus c, where g of v is that antiderivative provided provided it exists. Well, at this point, after we have evaluated this, we would replace v with whatever it was in terms of x and y. V was y over x, so you'd replace all the v's with y over x, and that would be your implicit solution. Okay, students, but know that if you stopped right here, if you got to this point and stopped, then you're going to get full credit. You're going to get an A, because obviously that's way too hard to evaluate. So what did we want to do? We wanted to separate the variables. And then once the variables have been separated, you would antidifferentiate both sides. Then we back substitute. Or in other words, we replace v with y over x. And then we're here. All right. So yeah, that is how we show that a differential equation is homogeneous polar. And that is the method for finding an implicit solution to the differential equation. But unfortunately, we weren't actually able to do it because that antiderivative was too hard. So you can use any one of these three methods to show that the differential equation is homogeneous polar. I used that one and that one. Once you do that, you let v equal y over x, solve for y, compute dy dx using the product rule. Write the equation in terms of v and x by substituting for this and substituting v for y over x over here. And then you're going to do some algebra to separate the variables. But that separating the variables almost always involves getting a common denominator on the right-hand side, because you're going to subtract the v from both sides. And then once you have a single fraction on the right-hand side, you're going to flip both sides and multiply by dv. And when you do, if you flip both sides and multiply by dv, you've got only x's on this side and only x's on this side, or only v's on that other side, excuse me. So this is where if you got to this point, you'll get full credit. So on our 4.0 scale, you're going to earn a 4.0 on the homogeneous polar standard. And then if we were able to finish the problem, if you had a different homogeneous polar problem and you wanted to solve it, after you separate the variables, you antidifferentiate both sides, and then you back substitute. You replace all the v's with y over x. And sometimes you can solve for y, sometimes you can't. If you can't solve for y, you just call that an implicit family of solutions and you're done, unless you have an initial condition. If you have an initial condition that's giving you an x value that goes with a y value, you could use that initial condition to find c.